Okay, sorry about that. So I was going to point out it's very strange that the first two natural frequencies, the lowest natural frequencies, were identical. That pretty much never happens, because it's like, well, which one does it favor shaking in first? What's the it's like the chance that a natural frequency is going to be exactly identical is almost zero. Well, the reason is because of all the idealized math. Our system, when we calculate the mass and stiffness matrix, it's notice the system is perfectly symmetric about the the xz plane and the zy plane. They're the same. You can rotate it 90 degrees, and it's perfectly symmetric. So, according to math, it's not going to be, analytical approach. It's not going to be able to tell the difference between those first mode shapes, and so of course it's going to be exactly identical. In reality, however, and by the way, even in this picture, I have bolts shown here that aren't on this side, so that would dramatically throw off the symmetry, and one of these directions would have a lower natural frequency. But just in reality in general, it's impossible for any system to be perfectly symmetric. So some atoms are going to be slightly different on one side than the other, and even with FEA, unless you take great care to mesh everything so that it's all perfectly symmetric, you're going to get slightly different values because the meshing algorithm is going to throw off your symmetry, and you'll get slightly different values. So if you did FEA on this, even without the bolts throwing off the symmetry, you'd have slight differences in these because the meshes aren't going to be symmetric. But of course, our analytical approach is perfectly symmetric, and it doesn't know the difference, so that's why they're identical. But in reality, you'll never get perfect symmetry, and so you'll never get exact values. But they can be very close. Okay? But there's always an order. There's the first natural frequency, the second one, the third one, so on and so forth, and they're associated with mode shapes all the way on up. Okay? And again, there are infinite mode shapes and infinite natural frequencies in reality, which I'll explain in a second. But for now, according to our analytical idealized assumptions, there's only 6. Okay? Because our matrix was a 6x6 mass and stiffness matrix. Okay, which has to do with the fact that there are 6 components in a twist and wrenches. Okay? Alright. Okay, so now let's look at stiffness matrices for general beam systems. So before, we really just talked about parallel systems. So you've got two state bodies directly connected to each other and in parallel, and so we calculated the stiffness and the mass matrix for that one. But now we're going to talk about how do you build a stiffness and a mass matrix for any of these, for serial and hybrid as well. And then if you can do that, then you can build a stiffness and mass matrix for any compliant mechanism, any flexible structure or anything really, whether you realize it or not. I'll teach you how to do this. Okay, so so first let's look at some theory here that is hopefully a review again from high school. But we'll take it another level, and you'll see how it applies. You know that anytime you have, so here you have your one-dimensional system. It can only move in one axis, along X, and with force here. And you've got springs here, and they have different stiffness, even though they look the same. This is K1, K2, and K3. You know these springs are in parallel if they experience the same displacement. Okay, so obviously if I move this up or down, since this is rigid, all these springs will have to move the same displacement. Will they have the same force in them? No, not at all. They will actually have different forces in them. Okay, so that's how you can know something is in parallel. And it's the same thing in 3 dimensions. You know, if you move a block with a twist vector, all the flexible elements stuck into the block, no matter how they're stuck into it, will experience the same twist vector. Okay, but they'll impart different resisting wrenches on the stage, just like this. Okay, so how do you find an equivalent stiffness? Well, you can say, what is the force in this? Well, it's x times k1. What is the force in this? Is x times k2. And what is the force in this? X times k3. So if the stiffnesses are different, obviously the forces in them will be different. And you just add them together, though, and they will add the total force. Okay. And so you can pull this Kx out, and you can see the equivalent stiffness, if you just treated this as if it was just one spring, you know, if you just wanted to find an equivalent stiffness that represented all three springs, well, it's essentially K1 plus K2 plus K3. So you would basically add stiffness together when it's in parallel, which is what we did, by the way, with our stiffness matrices for element 1, 2, and 3 from when we first introduced stiffness matrices. We added the stiffness matrices together because they were in parallel. Okay? Okay, so how do you know if a system is in series? Well, you know, so this system is in series, obviously. It's a one-dimensional system. Say we pull it with a force F. Is it true that even if K1, K2, and K3 are different, will all these blocks displace the same amount? No, they won't. But their force that's in them will be the same. Because if you think about it, if you draw a free body diagram and I cut these anywhere I want, and I have a force and this is all in equilibrium, if things aren't moving, if things are static equilibrium, well then the resisting force in any of those springs needs to be the same as the force I put on it. Okay? So you can know they all experience the same force. Okay, so just again, you know springs are in parallel if they experience the same displacement but different forces. And you know springs are in series if they experience the same force but different displacements. Okay? Alright, and so how do we find an equivalent stiffness for this? Well, we take that force we know is in all of them, and we divide it by K1, and that's now the displacement of this spring. F divided by K2, that's the displacement of this spring. F divided by K3, that's the displacement of this spring. Obviously, if we add all three displacements together, we get the total displacement, so you get that. Pull the common F out, and there we have, you can see, this is essentially compliance. Remember, the compliance of spring K1 is, well, let's not say this yet. If we invert this to the other side, then you can find the equivalent stiffness of this entire thing. K equivalent is the inverse of each stiffness added together. Okay, so you take this, invert it, now it's F equals Kx, where K equivalent is this. Okay? So, but going back here, notice that, remember, the stiffness of a spring is K, right? It's what relates F equals Kx, right? The compliance of a spring is the inverse of K. It's 1 over K. That's the compliance of the spring. So you can see, whereas in parallel, springs in parallel, you add their stiffnesses to find an equivalent stiffness. In series, you add their compliance. So the compliance of K1 plus the compliance of spring 2 plus the compliance of stiffness of spring 3, you add their compliance, and then this is F times compliance equals X. That's the compliance of the entire system. Okay, so when springs are in parallel, you add their stiffness. When springs are in series, you add their compliance. Okay? And that's how you find the equivalent stiffness or compliance of the spring. Okay? Okay, so say I had this it's again an idealized one-dimensional system. Say everything, the stage and all the bodies could only translate up. Okay? And say we want to find an equivalent stiffness system. So say we've got all 7 springs here of all different stiffnesses, and I just want to find what's an equivalent scalar stiffness that describes this stage. If I want to put a force on it and I want to relate it to its displacement, what F equals, or what K times that displacement equals to F. Okay? Well, you can put me on pause and use principles of parallel and serial to add the scalar stiffness values together in special ways so you can calculate this equivalent. Okay, so go ahead and put me on pause and do that after what I just taught you. Okay, welcome back, and here's the solution. Okay, so because these are in parallel, you invert, or so you just add them. So there's K1 plus K2, great. But now that combination is in series with this, so you take K3 inverse plus the sum of these inverted, add them together, invert it, that's the stiffness of this. Okay, you do the same thing with this to find the stiffness of this, and you add it because they're in parallel, and then you just add it with this because it's in parallel. And then you just plug those scalar values in and you get the equivalent scalar value. Okay, so that's how you deal with springs for simplified one-dimensional systems. Okay? Okay, but now what if you have a three-dimensional crazy system? This is a hybrid system. It's got 3 limbs that are basically in parallel. And notice it's the exact same schematic. If I drew a schematic, there's this stage and 2 intermediate stages, this stage and 2 intermediate stages, or intermediate bodies, right? And then you'll notice this is 1 and 2, this is 1 and 2. That's 3, that's 3. Okay, 5 and 6, 5 and 6. Here's 4, here's 4. And then the 7 one off by itself. So this is literally a schematic of this potential 3-dimensional system, where here is your global coordinate system, okay? So the cool thing is if you understand how 1-dimensional systems work, all the same math applies to our stiffness matrix. Okay, so what we do is, let's say we want to find the stiffness. Now before I only taught you how to find the stiffness matrix of parallel systems. So now this is a hybrid system, and you know, you find it the same with the serial system or really any system. What you want to do is find the stiffness matrix of each element, the 6 by 6 stiffness matrix of each element. And so say we want to find the element 1's stiffness matrix. Okay, remember, look up in my theory that this is how you find that stiffness matrix. Okay, and the way you would do it is you could, you know, to find, well, you know how to find delta, that's given. You know how to find the S, that's from our convention of the single rectangular prism. Okay, but how do you find N1 and N1 inverse? Well, N1 consists of an L vector, N1, N2, and N3, where you draw from your global coordinate system with respect to the global coordinate system some L vector that's where it attaches to the stage, and then you do N3 into the stage, and then N1 and N2 perpendicular to these rectangular prism faces, and make sure they follow the right-hand rule. Okay, and again, N1 could have come out here, N2 could have, you know, whatever, right? But it's really important that N3 is the one going along the axis into the stage, and you do your thing with N1 and N2. And notice it follows the right-hand rule. So you could have done that. Did you also know that, here's what I didn't teach you, we just did it with, you know, it was a parallel system, and it goes from the ground to the stage. We're interested in the stage, so I think you always just assumed you point L to the thing that attaches to the stage. But you could have equally pointed to the L to the other end and done N3 going out of it into this body, and arranged N1 and N2 how you liked as well, just as long as N1 and N2 follow the right-hand rule. Okay, so the end that you pick, it doesn't matter. Trust me, the math ends up all being the same. Okay, so regardless of what thing you're picking, say you want to build the stiffness matrix for 5, well, you could have an L vector that points to there, or have an L vector that points to where it attaches on that end. Do your N1, N2, and N3. Make sure N3 goes out of the element into the body, and make sure you orient N1, N2 so they're perpendicular to the faces and follow the right-hand rule. Okay? Regardless of which N you use, you will get the same stiffness matrix, K1 or K2, K3, K4, K5, K6, K7. Okay? Yeah, this is all saying what I just told you. Okay? So once you find those stiffness matrices for each element, okay, using this equation, then what you can do is, if you want to find an equivalent stiffness matrix for the entire thing, okay, then you can use the exact same math. Okay, so look, if you go back and look at the one-dimensional scenario that has the exact same schematic, look, K1 plus K2, invert plus K3, invert, and you go through and do all this stuff, you can do the exact same thing, except it's just with matrices. K1 plus K2, and then the whole thing inverted, plus K3 inverted, put it in parentheses, invert that. And do this, and then you go back and look, you'll see this is exactly the same. The only difference is, instead of scalar stiffness values, you're using these 6 by 6 matrices. Okay? That will find an equivalent 6 by 6 matrix that can relate a wrench on the stage to a twist of that stage. So if you want to do a displacement load, say you impose a twist, assume this point is stuck on this stage, and you give it 3 rotations, 3 translations of how you want that stage to move, or how you want this point on that stage to move, and you times it by this equivalent 6 by 6 matrix, it'll tell you what wrench, defined with respect to this, you need to load that stage with. Or if you say, I want to load this stage with this wrench, you could take that, invert this, times it by that, now you find how much the stage will displace with respect to that. Or it'll tell you if the displacement of that point if it was stuck on that stage. Okay? And again, you can use a transformation matrix. Say you wanted to know how this point moved, you use a transformation matrix to get from that twist to that, that twist or something. The 3 rotations, 3 translations of that point, right? So you can see how this could be very useful when you want to actuate something. So when you do parallel systems, I taught you, you can find the stiffness matrix of each of the elements and add them together, right? Well, if you have now a hybrid or serial or any other combination, you just find the stiffness matrix of each element, and you can use these spring laws of parallel and serial and find an equivalent stiffness matrix. Now, the one thing you can't get from this setup is you can't know how this stage will move or how this stage will move. And you can't load this stage or this stage. Like, wouldn't it be nice if we had a theory where we could put a wrench on this, a wrench on this, a wrench on that, and know how all three of them move? When we do this equivalent principle, we can just know how this stage moves. And it's the same thing with the one-dimensional thing, right? By turning this into an equivalent stiffness, we can't know anything about the internal stages. We can only know about the final stage we care about. Okay? So this is a nice way that you guys can solve this, okay? All right, but I'm about to show you a way that you can know how those intermediate stages move, and it's not too complicated, okay? And I'm going to give you a tool here. All right. Okay, so say you have this system, okay? Now say we add this. Say we interconnect these intermediate bodies with a spring here. Now find an equivalent stiffness of this stage. Okay, so put me on pause. So the only thing I changed is I interconnected these intermediate bodies with another spring, K8. I've added a spring. Can you use rules of series and parallels and springs to find what K equivalent is of this whole system? You know, so if I just drew the stage with a big equivalent spring down to ground, can you find that? Okay, put me on pause and try it. Okay, hopefully you're tuning back in and you see that it's not doable. Okay, and the reason is because you can't break this down into parallel and serial subsystems, because now this is called an interconnected hybrid system. You have interconnected intermediate bodies, and as a consequence you can draw loops through the springs that don't ever pass through the ground. Okay, these are interconnected, and so you can't use that trick. You can't find a 6x6 equivalent stiffness matrix that tells you this about the stiffness of the whole thing. Okay, so that approach only works when it's a parallel serial hybrid, but not interconnected hybrid that I just taught you. Okay, so but now let me teach you. That's what this essentially says. Now let me teach you an approach that can work for anything. Okay? So again, notice this schematic. We're going to use the exact same three-dimensional thing we did before, except we're now interconnecting these with a wire flexure, which I call 8. Okay, so see, we're connecting those stages with K8. That's the new change. We did that there. Okay? So this is the three-dimensional world here. Okay. All right, so let's label these stages. So here's the ground, G. Let's label these stages B1, B2, and B3. Okay, body 1, body 2, body 3. What would be nice is if we had a theory that allowed us to load any of these bodies, like wrench 1, wrench 2, wrench 3. That's the 3 wrenches imposed, all defined with respect to this global coordinate system, but loading those independent stages. And then it would be nice if we found a stiffness matrix that related all 3 of those wrenches to the 3 corresponding, twists, of course all defined with respect to the global coordinate system, but of body 1, body 2, and body 3. Or to do, a displacement load and find out what the wrenches would need to be on all 3 of those things to get it to move that way. That would be awesome, okay? Well, let's just say we have that. The way it would mathematically be packaged is as a, if there's 3 bodies, which is the case here, you take all the number of rigid bodies and subtract 1 for the ground, so 3 movable bodies, and let's call that B, for instance, and that means we want to track B twists, so in this case it would be twist 1, twist 2, and twist 3, right, and that would be an 18 by 1 vector because each twist is 6 components, 3 rotations and 3 translations, so this would be an 18 by 1 vector, or, and then let's say the stiffness matrix is an 18 by 18 matrix, because it would have to be, right, to multiply this 18 by 1 vector to then get an 18 by 1 output vector, which is your wrenches. W1, W2, and W3. Okay, so the new stiffness matrix, whatever it is, if we could make one that again just assumes all the masses have are infinitely rigid and all the elements have all the compliance and stiffness, and we use the stiffness matrix of each little element, and we could somehow construct it within this giant matrix where now this is no longer just a 6 by 6 matrix, but a 6B by 6B matrix, where B is the number of these movable bodies, so 18 by 18 in this example. That would be awesome because we could relate these. Now we could impose twists on this and we could times it by that and get the wrenches out, or we could take this and invert that and get that. This was the true twist wrench stiffness matrix for any parallel, serial, hybrid, or interconnected hybrid system. Okay? And it does exist, obviously, and you know, you can look at this paper I published back in 2013 that tells you for any general system how to construct this, this stiffness matrix. And I've also coded a MATLAB script that you describe how many elements there are, where they're located, what bodies they join, and what their geometry, material properties are, etc. Their locations, orientations, and all the things it needs. And then it just constructs this matrix for you. So it's beyond the scope of this course for me to teach you how to construct this matrix. In a future follow-on course to this course, I will be teaching the theory of how to make this matrix. But for now, if you're curious, read this paper. It goes in nauseating detail how you make those. If you're not curious, you can just get my script, that I will provide on my website. That tells you, it's a MATLAB script that has you tell it how many elements, what they connect, their location, orientation, all these things, and it will construct the stiffness matrix, okay? And it will do this, okay? So how would you use such a stiffness matrix? Okay, well, like for instance, okay, well, I mean, just like this, right? So if I give you a displacement load, you multiply it and you get this. If I give you the load, and you just invert it, now you find out how they move displacement-wise as a consequence of those loads. So let's do that. Let's say I wanted to put a pure moment on the stage, which is body 3. So I'd put omega 3, and it would be, it's defined with respect to this coordinate system. So it's collinear with the z-axis. So that moment would be 0, 0, 0, 0, 0, 1 Newton meter. Okay. And you would, if you stacked it in here, you'd say, say we want no wrench on these bodies. So these first two would be 6 zeros, these would be 6 zeros, and the last one would be all zeros except 1 Newton meter. Okay, like that. And then you times it by the inverse of the stiffness matrix that you could build from the description of these wires and how they connect and what they're made of, etc. My script will generate that stiffness matrix. Times it by that, and out will come, you'll know the twists of all 3 of these bodies. In other words, the 3 rotations and the 3 translations of this point if it were attached to any one of those bodies. Okay? So T1 will be the 3 rotations and the 3 translations of that point if it were stuck to body 1 as it twisted around this line of axis, right? And this one would be the 3 rotations, 3 translations at this point if it were stuck to body 2 as it moved around its twist, and this would be same thing with body 3, right? So, but if you only care about twist 1, then you only need to look at the first 6 components, okay? And if you then wanted to say I wanted to know, well, what about that point? How does it move? Well, now you'd have to draw an L vector that goes from there to there, define your n things, for the coordinate you want to define it by, construct an n matrix, and then invert that n matrix and times it by T1, and that will produce the 3 rotations and 3 translations of that point caused by this one moving, which is caused by that moment, defined with respect to that coordinate system. So that should show you how this can work, okay? And again, sorry I can't teach you how this is made. It's just beyond the scope of this course, okay? I'll teach it to you in another one, but all you really need is to know generally how it's constructed from what I've taught and then how to use it, okay? Okay, so now let's look at the mass matrix for a general scenario, okay? So before, we just looked at how to make a mass matrix for a parallel system, which just consisted of 2 bodies where one of the bodies was grounded. So you really just do a mass matrix of 1 body. Well, what you do for a hybrid or serial system is, again, you don't have to make the mass matrix for the G, the ground body, but you do construct the mass matrix with respect to this coordinate system for body 1, body 2, body 3, and as many bodies as can move. And then what you do is you just stack it in a giant, again, 6B by 6B matrix, okay? That's the same size as the stiffness matrix, that where, again, B is the number of bodies that can move. So in this case, 18 by 18 matrix, where it's kind of like a diagonal matrix, but it's not diagonal formally. But what you do is you take body 1, the 6 by 6 matrix, and put it here. Body 2, the 6 by 6 matrix here, and you keep going until you get to body M, the 6 by 6 matrix here, and the rest is all 0. Okay, so it's kind of a diagonal matrix of 6 by 6 matrices, but of course that's not a true diagonal matrix. Okay, so that's what you do to build the mass matrix of the entire hybrid or serial system. So it's much easier than the stiffness matrix. That is teachable. Okay, what's not teachable and outside the scope of this course is how to build a mass matrix of any stage that is an arbitrary strange shape that doesn't have clear principal axes for the mass moments of inertia. That's again, I'll teach that in another course that's more advanced. Okay, but this gives you a pretty darn good idea. Okay, and so let's look at the equations of motion for serial or hybrid or any systems. This is an interconnected hybrid system. Again, it's the same thing. It's F equals mx double dot plus kx, right? Assuming there's no damping. You just have your giant 6b by 6b mass and stiffness matrix, and you have your 6b by 1 vectors, where these are the accelerations, those are the displacements, and those are your loads. And that's the equation. And again, you could plug in a guess. That's the A cosine omega t, and you would get this equation. And you can see where this is going. You would essentially, to find the eigenvectors and eigenvalues, you would take this giant M matrix, invert it, times it by the giant K matrix, and now you get a matrix that you find the eigenvectors, eigenvalues, you square root the eigenvalues, and now you have natural frequencies corresponding with mode shapes. Okay? And here's the interesting thing. Remember, these matrices are no longer 6 by 6 matrices. They're 6b by 6b matrices, where b is the number of those bodies. So for this case, if we assume all the masses in the stages, and we assume all the compliances in the flexures here, because there's 3 stages, we're going to have an 18 by 18 M inverse times K matrix that we're taking the eigenvectors and eigenvalues, which means we'll have 18 mode shapes and 18 corresponding natural frequencies. Okay? And for every body we add, we're going to increase the number of mode shapes and natural frequencies. Now, this allows me to explain why real systems have infinite natural frequencies, infinite mode shapes, because if you think of it, you could model, you could keep breaking it down, you could say, oh, let's put a pseudo-rigid stage here, and now we have a new stage, and here's half a flexure, and here's half a flexure. Let's do a pseudo stage here, and here's half a flexure, here's half a flexure. You keep breaking it down and adding more stages, and connecting it with these flexures, and that's how you'd essentially do it. You'd break it into more finite elements, and until you finally break it down into atoms and their atomic bonds, where the nucleus is the mass and the bond is the stiffness, and now you just keep adding more natural frequencies and mode shapes according to the analytical theory. So if you could model this as just trillions and trillions of atom masses joined together by little atomic bond springs, then you'd get a giant trillion by trillion something huge matrix of mass matrix and stiffness matrix, and that would produce that many natural frequencies and mode shapes. So that explains why in reality, reality doesn't model things as having lumped masses and lumped compliance. It's everything has some compliance and some mass, and it's all distributed. And so as a consequence, it gets infinite natural frequencies and infinite mode shapes. Okay. And so with that, you guys know how to make the mass and stiffness matrix. You know how to, for most systems, pretty much, with some caveats on the simplification of the stage and the rectangular prism elements, and I suppose I didn't teach you how to make the big stiffness matrix for interconnected systems, but anyway, you know, you have a paper to it now, and now you can find natural frequencies, mode shapes, and you can load things, you know, quasi-statically or with some speed. You know, if you wanted to consider the mass matrix, and find how all the bodies in your system will move as a consequence of wrench loads and those kind of things. So. Okay, so with that, that's the end of this lecture. Congratulations for surviving it. There's no more horrific math. The rest of the course is really fun. Please don't drop the course. It's an awesome course from here on out. And again, I apologize for the audio quality. Thanks for watching.